everyone. So we're going to go over some common resonance patterns. You can never say how many arrows you're going to have to put. I know a lot of you have been approaching me with the question, how many arrows should my resonance structure have? I see some with 2 arrows, some with 1, some with 3, and there's never a straight broadband answer I can give to you on that. But what I can talk to you about is some patterns that you can look for. So when you see a bunch of molecules on your midterm and you want to assess which ones display resonance, you can kind of look for these 5 key patterns. Again, don't memorize, analyze each molecule on its own. And we'll start with our patterns. The first one is a lone pair next to a double bond. So I'm going to draw our example here. In this case, we have our electron-rich region, lone pairs on oxygen, right next to a carbon that has a double bond. So what you can do is you can start your arrow tail at the region of electron density and move it down to this relatively electron-poor area. But now you have violated your octet rule for that carbon. So what you're going to do is include a second arrow and move this region of electron density out onto the carbon. And that gives you your second resonance structure. So this brings us to the idea of relative importance of resonance structures. With benzene, both molecules contributed equally to benzene as a whole. But in this molecule, you have in this structure, you have one molecule that's more significant than the other. So you have a neutral molecule up here, and you have separation of charge down here. And so your molecule that has your least separation of charge is going to be your most significant. And moving on to your second pattern, a positive charge next to a double bond, I'm going to draw out a conjugated system. I'm going to put my positive charge on this carbon and go ahead and put my resonance arrow. So over here we have a region of electron density over here with our pi bond. And we have a carbon that's relatively electron poor. So we can take our arrow and move this bond over here. And that would create our new resonance structure. With our positive formal charge now associated with the carbon in the middle. Now notice we did not trace our positive charge with our arrow. That's a common mistake that people see on midterms, is instead of putting your arrow this direction, you'll start with your positive charge and then move it that way. Again, that is wrong. Your curly arrows must trace electron density, must trace electron flow. And this was a conjugated system. We had a single sigma bond, a pi bond, sigma, pi, sigma. So that means when you have this conjugated system that you're going to have more possibilities for resonance. So we have another possibility here. We have an electron-poor region, and we have an electron-rich region right next to it. So we can take our arrow and show our movement of electrons over to there. Again, the neater notation would be to put your arrow all the way in the center over there and create this structure where your positive charge is now associated with this carbon. And those are our resonance structures with a positive charge next to a pi bond. Our third pattern is going to be a lone pair adjacent to a positive charge. Another oxygen example. And a positive formal charge on this carbon. So we have electron density over here in this carbon area, this oxygen area, and we have an electron-poor region in this carbon area. So we can share some of oxygen's electrons with this carbon over here, creating a new resonance structure that looks like this. Again, I'm going to talk a little bit about the significance of resonance structures. You never want to have a positive charge on electronegative atoms unless that electronegative atom has a complete octet. So over here, we have our positive charge on our oxygen. And that's OK in this case because we have a complete octet. 2, 4, 6, 8 electrons. But you'll not see a nitrogen or an oxygen have a positive charge if they don't have a complete octet. So our fourth pattern to look for is a pi bond between two atoms of differing electronegativity. So here we have our highly electronegative oxygen atom right next to a carbon atom. And since oxygen is more electronegative, it's going to be more greedy. It's going to pull those electrons towards it. So you can create a resonance structure in which you move these pi bond electrons up to this oxygen, giving you this. Oops. Again, remember your formal charge. This structure is going to contribute more to the overall molecule than this resonance structure because here we have a separation of charge. We have our negative charge focused on our oxygen, and we have our positive associated with the carbon. And here we have no charges associated with any of the atoms, and minimal separation of charges is better. For our last pattern to look for in resonance problems, we have a conjugated system of pi bonds in a ring. Now this brings us right back to benzene that I had on the board earlier. Again, conjugated system, pi bond, sigma bond, pi bond, sigma bond, this alternating system within a ring. And all you do in problems such as that is you shift each pi bond over one. So we did that with benzene. We moved each double bond over. And those are the patterns for resonance.